Alright, the next thing that we're going to talk about here is moving around a circle with a constant speed. So if you're this little red circle here and you're going around a circular path, interestingly enough, there must be some kind of force associated with this motion. And the idea for that is relatively straightforward. If you're at this particular point, which I'm going to mark in green, your velocity is straight upwards. Alternatively, if when you get to the top of your circular path, so you're at this position here in orange, your velocity is this way. This implies that there must be an acceleration and thus a force because your velocity has changed. Keep in mind that accelerations are caused whenever your velocity changes, and that includes direction. So even though your speed or how fast you are going is constant, if you've changed direction, there will be an associated acceleration. And thus, if there's an acceleration and your object has mass, there will be a force. Now, I will save you some of the mathematics, but this particular force has two main interpretations. So we're going to go through the formal one first, and then we're going to go through the more useful one afterwards. So let's say that you're here, and you're an external observer. So you're outside the system. That's my best approximation of you. And you're taking a look at this. If you take a look at this system, what you will notice is that your acceleration, and thus your net force, must be radially inwards at all points in time. Right? So if you're sitting outside the system looking at this thing, when it's over here, you're going to see it get pulled towards the center as it's moving upwards, and when it gets up here, it's going to get pulled downwards. And if you don't believe me, you can test this yourself. What you can do is you can take a piece of string or anything that has a flexible length, hang a weight off the bottom, and spin it around in your hand. So let's shrink this so it's like to scale, and spin it around in your hand. What you'll notice is you will actually feel a force that you have to exert. In other words, you'll have to pull inwards on this all the way about its motion. And so this is something that you'll see. Now, in terms of this force here, we can relate it directly to the tangential speed, or how fast you're going around the outside of the circle, as well as the radius of your circular. And that's what you'll see in the top left of your screen here. So you can take the mass of your object, multiply it by the tangential speed squared, and divide it by the radius, and it will give you the magnitude of this force. However, as you are looking at this from the outside, you see this acceleration, and that means that for this particular case, this centripetal force, which is inwards, has to equal to the net force, because it's associated with the acceleration that you see. So this is one of the main interpretations about going around a circular path. It's known as the centripetal picture, and it is the technically correct picture because it is seen by the external observer. So if you're the external observer, you see this thing go around in a circular path, you notice that there must be an acceleration and a force inwards, and because that's an acceleration that you are seeing with your eyes, that centripetal force must equal to the net force. Now, there is a second picture here, which is actually significantly more useful if you're trying to figure out what's going on. Because, interestingly enough, it is the force that you picture. So we're going to reset this, and we're going to talk about what happens if you are, instead of being outside the circular path, you are inside. So we'll draw you inside the object that's moving around on the circular path. So you're moving along with this thing now. Now, interestingly enough, this is something that most people have done. If you're in a car and your car is moving upwards here, and you take a really sharp corner, you will actually feel to you what appears to be a force that pushes on you. Now, if you go around the circular path, like so, the force that you feel will actually be outwards. If somebody takes a sharp left, you actually get thrown outwards. So if you're taking a look at the force as you would see it, if you're over here, you'll see a force pushing you outwards, radially outwards too, along each part of your pathway. So this is the force that you inside feel. Right? So if you were looking at yourself inside this red circle, here you would see yourself be thrown to the right, here you would see yourself be thrown upwards. This here is actually the same idea we just talked about. However, because it is viewed by a different person and has an effectively different direction, it's outwards as opposed to inwards, we call this the centrifugal picture. And this is the same centrifugal that is present in a centrifuge, or a centrifuge. I can't even say the word right. Centrifuge. If you have people or cells or DNA or anything inside a centrifuge, and you spin it around, you'll notice that the contents of the centrifuge all get pushed towards the outside edge. Interestingly enough, this is based on the same effect, so it has the same magnitude calculation. You can still take m, multiply it by the tangential speed squared, and divide it by the radius. The only difference here is it is going to be a outward force. In addition, for this picture, the centrifugal force is simply an additional force. It's not the net force, it's just an extra force that you add into your system. All right, so if you're taking a look at a centrifuge, in this picture, this centrifugal picture, what you'll say is there's simply a force that is introduced that acts on the contents, or the internal contents, of the thing that's moving around the circular pattern and pushes it towards the outside edge. At the end of the day, you can solve these problems with either of these pictures, but it's up to you to pick the one which makes the most sense to you. For the example problem in this section, I will actually do it both ways, get the exact same answer, and you're allowed to pick and choose. I will caution you, though, that if you're reading your textbook, it does not like this centrifugal picture. That's because this force that you see that pushes you outwards is a fictitious force. In other words, it's caused more due to the fact that you are in an accelerating frame of reference, because you, the observer, are actually accelerating in this case, as opposed to you being outside the system, being able to look at this thing and not be accelerating. And fictitious forces show up relatively consistently whenever you have changes in references in Newtonian mechanics. Anytime your frame of reference is accelerating, Newtonian mechanics can add in these random fictitious forces because it cannot distinguish them based on the point of view. Now, most people prefer the centrifugal picture, especially with the more biologically minded people of you, because this is literally a centrifuge. If you have a little micropipette here, and you have some DNA squiggles in it, and the thing spins around with some kind of speed, what you'll notice is the contents of the centrifuge get pushed towards the outer edge of this. And that's, typically speaking, the frame that a lot of people find make more sense when they're looking at these particular problems. But for the purpose of this course, you can use either one. They come out exactly the same. Just keep in mind, for the centripetal picture, your force is inwards, radially speaking, and it must be equal to the net force. In the centrifugal picture, the force is outwards, and it is a completely external force that you can just add into your system. And it explains how most spinning systems work. Anytime you spin something, you're changing its velocity, therefore there must be an acceleration and associated force in some way, shape, or form.